Please pause the video to see any information in the upcoming 2 slides. To introduce the lab, I want to recall some important theory used in the motion of the tape roll. The first important law is Newton's first law, where an object at rest remains at rest while an object in motion remains in motion unless acted upon by an outside force. What this means in relation to the experiment is that after the initial force is enacted on the object, it should remain in its condition of constant velocity for the duration of the motion. Secondly, we must recall Newton's second law. This law states that the time rate of the change of the momentum of a body is equal in both magnitude and direction to the force imposed on it. However, what does this really mean? This means that we can use the momentum update formula derived from the force formula as seen above, because F naught is equal to the change in momentum over time, and subsequently we can find the velocity update formula. It is important to note that the net force of an object is 0 when velocity is constant. This is because there's no acceleration or change of velocity over time, making the magnitude of the net force 0. An additional important formula we can derive from the velocity update formula is the position update formula, as seen here. This allows us to predict the final position vector of the mass using the average velocity. In fact, all of the update formulas allow us to predict their final positions and quantities. Finally, we must identify the assumptions we have made for this experiment. First, we assume that there are no outside forces enacting on our system from the surroundings. This means that we can completely ignore friction forces or drag. We also assume that this is a point mass and is traveling in one direction only. As it can be seen, the motion of the tape is traveling horizontally in a negative motion in relation to the origin. Additionally, from the model generated in the tracker, the position of the tape against time is relatively linear, which indicates that the velocity is constant as the position of the tape is changing at a constant rate. As it can be seen from the tracker motion, the velocity of the tape roll was negative 0.5529 meters per second. Keep this in mind as we continue to the computational model as calculated from below script. Pause the video to see any calculations made for the average velocity. In order to derive the computational model, we must use the initial conditions as displayed in 2b. The code essentially transforms the data into a momentum update formula as seen in the code, and then subsequently the velocity update formula, and so on. Thus, putting a 0 net force input transforms the momentum update formula into a velocity update formula, and this gives us the computational model. Feel free to pause the video to look at this code further and copy the link to see the code itself. As it is seen, the conclusion was that the final and initial velocity of the tape was negative 0.5696 meters per second. Simultaneously, this model shows the velocity is constant as seen in the right-hand image. This shows that the net force is 0 due to no change in velocity, indicating no acceleration. This is seen easily by the fact that the velocity over time graph is just a constant number via a straight line. When comparing the actual motion found from the tracker versus the computational model, it can be seen that they have two very different velocities. This is found by the equations of the lines where velocity is the gradient of the line. This is because the gradient is the change of the position over time, which is equivalent to velocity. However, the most important conclusion is that the velocities are different. If it was true that there were no outside forces interacting with the tape, the velocity would be the same for both. Thus, there are possible errors in this experiment that make the velocity not actually constant. These include other outside forces such as friction causing the tape to decelerate and causing the net force to not actually be 0. Thus, we can conclude that the actual data could be decelerating as other forces are involved, which explains why the data itself is not linear. We can also conclude that the computational model is perfectly linear as it doesn't account for these errors, making the data perfectly linear, which shows constant velocity. As noted in the tracker footage, the origin of the vectors was put to the left of the object's initial position. However, as the object traveled towards the origin, as it did, the velocity was negative. However, if the axes were flipped so that the tape traveled in the positive direction, the only change would be the direction and not the magnitude of the vector. This means that velocity would be positive and not negative, but would have the same magnitude. This is because the same distance would be traveled over the same amount of time, while the displacement, which is a vector quantity, would indicate a positive motion. This also means that the gradients of the line would be positive in an upward slope, as indicated by the red line. Finally, is it possible to justify that the net force is 0? Unfortunately, it's not possible because we do not have the necessary information to determine this because we have not taken into account every interaction our system is experiencing. Instead, we have just focused on the velocity vector. The only justification we have is that the data shows a near constant velocity, which is indicative of a net force of 0. Thus, to answer this, we would need to interpret and calculate the other force interactions the tape is experiencing via a free body diagram or other experiment. Thank you for listening.